Well, all right. In this screencast, we try to explain to elementary educators what we mean by equivalent fractions, what it means to say that two fractions are equivalent. And so we should probably take a look at what fractions are in the first place. I have included for you in a file fraction bars. These are little fractions. This is a third, this is a fourth, and all of this makes sense because 2/2 equal 1 whole, and 3/3 equal 1 whole, and 4/4 equal 1 whole. And so you can see how each of the fractions in the document I sent, each of these fractions represent a part of the whole. And these are all the common fractions that people tend to work with in elementary school. So some questions to consider in this screencast. Why is 1/3 called 1/3? Pause, think for a moment. Why is 1/3 called 1/3? Well, there's a whole. Why is 1/3 called 1/3? Because if we have 3/3, then those 3/3 equal the whole. 1/3 is called 1/3 because it's one part out of 3. It is almost like we took this 1 whole and broke it into 3 equal pieces, and this is one part out of a whole with 3 parts. That's why 1/3 is called 1/3. So how can we model 2/5 or 3/8? Think for a moment how we might use these pieces to model 2/5 or 3/8. As you might imagine, 2/5 is literally 2/5, and 3/8 is literally 3/8. We'll make this on infinite cloner so it's a little easier. 2/5, 3/8. 2/5 is literally 2/5, and 3/8 is literally 3/8. By the way, what's bigger, 2/5 or 3/8? Well, it appears that 2/5 is bigger because the pieces that make up 2/5 look like they take up a little more space than the pieces that make up 3/8. Now, more advanced people are going to recognize that this is about 0.4, and this is about 0.375, and 0.4 is bigger than 0.375. But you can see in the fraction model, the 2/5 is bigger than the 3/8. So how can we model that two fractions are equivalent? So take a moment, pick two fractions that you know are equivalent, and then decide how to model that they are in fact equivalent. Like hit the pause button, do it with the models that you have before you. So we could go with the standard, not 1/3. We could go with the standard 2/4 equals 1/2, right? We could play that game. Here's 1/2. Here's 2/4. What do we notice about 2/4 and 1/2? We notice that 2/4 appears to equal 1/2. And you can do this with any two fractions that you know are equivalent. If you line them up, the fractions should be the same. For example, we know that 4/12 is the same as 2/6. How do we know that 4/12 is the same as 2/6? Well, if we play this game, 2/6. Here's 2/6. 4/12. Here's 4/12. Boy, that's an image problem, isn't it? That's a serious image problem because those are supposed to look like this, and they very clearly don't. And that is a problem with my image and how things got cut and pasted. It's probably better with your model than it is with my pictures. Ugh, teaching in 2020. Anyway, but this is how we model that fractions are equivalent. And if our blocks are the sizes they're supposed to be, then we can demonstrate that 4/12 is in fact 2/6. Okay, there's going to be another screencast that's going to talk about how we do this without the model, but this drives home the idea with a model of how fractions are equivalent.